We know from Faraday's law of induction the strength of the voltage induced in a loop. We know that it's proportional to the rate of change of magnetic flux through that loop, and it's also proportional to the number of turns that you apply to that loop. But we haven't yet discussed the direction. Does it go clockwise or anti-clockwise? And there are so many right-hand rules in electromagnetism, it would be very confusing if we were to add yet another, and there are so many different things you'd have to add into your mind to get this correct. But it turns out there's a really simple way of figuring it out using the conservation of energy. Using the conservation of energy when you're talking about induction is usually described as following Lenz's law. It was developed by Heinrich Lenz in 1834, before the ideas of energy and conservation of energy had really reached their final form, though these days we can see that they are one and the same. So Lenz's law states that you can't get something for nothing. If I have a coil making a magnetic field, and then I have another coil that's going to have a magnetic field induced in it. Now if I'm putting current in that first coil, it's going to make a magnetic field that reaches right down into the second coil. And remember that this is often helped by having a bar of some ferromagnetic material running through the two of them. However, the key point is, when we change the current, we're going to change the magnetic field. And when we change the magnetic field in the first coil, we change the magnetic field in the second coil, and that changes the flux flowing through it. And that's going to induce some kind of current in the second coil. And the question is, which way should it go? So if we take an example that this current increases, if that current increases, that's going to increase the strength of the magnetic field, which means it's going to increase the amount of magnetic flux going through the second coil. Now, if an increasing magnetic flux going through that coil caused a voltage that would increase the magnetic field even more, then it would have a runaway effect. We'd have more flux, so we get more of that voltage, and so we get more current, so we get more magnetic field, and so we get more of that voltage, and it will go on to infinity. And so that obviously can't be the way it works. And so the voltage that's induced has to make a current that resists that magnetic field change. So to resist the flux going up, we need some magnetic field made that way. And if I look at that and that wire, I see that I need the current to be going out of the page here, and that will make a magnetic field that goes up. And so I'm going to need the current to be flowing in that direction around this loop. And so we're going to have a potential going in that direction. And so if the magnetic flux is increasing, we know that the potential has to be going that way, and if the magnetic flux is decreasing, then it would go the other way. We can see a particularly clear and practical example of Lenz's law if instead of looking at transformers, we look at magnetic braking. So what I have here is a metal disc that's free to spin. Okay, so it spins happily. Now, if I were to put that in a magnetic field, it would be a conductor moving in a magnetic field, and so we'd expect, from Faraday's law of induction, that eddy currents, little circles of current, would be induced inside that disc. And they would, in turn, produce their own magnetic fields, and the question is, in what direction are they going to do all that? And the answer is very simple. They have to oppose the motion, don't they? And so if I just put this magnet around that disc, it stops the disc rather rapidly. This is a nice strong magnet, and indeed it didn't involve any touching. If I show you directly, you can see the disc spinning. There it is, spinning nice and fast. As I bring the magnets in, the magnetic field induced a current that opposed the motion, and so what we ended up with was a stopped disc with no touching. And that's magnetic braking. It's a very handy tool. And again, this is just a restatement of the conservation of energy. If magnetic forces that were induced helped the motion, helped accelerate the motion in that direction, then of course you'd be getting kinetic energy out of nowhere. We can do another fairly clear demonstration that what's going on in magnetic braking is in fact to do with currents being induced inside the material. And the way we do that is we have magnetic braking where we have different materials. So what we've got here is we have three magnets at the bottom here. And those three magnets are in tubes, and there's plenty of room for them to slide down those tubes. But those three tubes are made of different materials. We have clear plastic, which is not a conductor. We have aluminium, which is a conductor, and copper, which is a really good conductor. And so what I'm going to do is I'm going to take this, I'm going to tip it upside down, and then each of these three magnets will just slide down the tube into the other end. Okay, and let's see how long that takes. Extremely different times. You'll see the plastic went down, bang, the aluminium came down a bit slower, and the copper was surprisingly slow. And indeed, if you take these and make them cold, resistivity goes down as you make things colder, and so you can find that the currents really, really slow the motion of the magnets, and it gets slower and slower as you make them colder.